Okay, Organic Chemistry 2330. We are going to continue on with our adventures in organic chemistry with chapter 15. We're going to have 4 videos all related to enolate ions and the reactions of which they do. Okay, so this is a continuation on to the different things we can do with carbonyls. Up to now, we've been reacting that carbonyl or substituting that carbonyl by adding across aldehydes and ketones or using the acidity of the carboxylic acid or its derivatives. Here, what we're going to do is use the carbonyl as an activating group to activate the carbons next to the carbonyl to do reactions, okay? So what we call the carbons next to the carbonyl are called alpha carbons, and the hydrogens that are bonded to those alpha carbons are called alpha hydrogens. Now, the reason we're interested in those is we don't actually want to do work on the carbonyl directly. What we want to do is use the carbonyl as an electron withdrawing group to increase the acidity of those hydrogens on the carbons next to that carbonyl. So if we think about it, those alpha hydrogens next to those aldehydes and ketones and esters are more acidic than if they were alkanes or alkenes because the carbonyl is acting as an electron withdrawing group. But they aren't as acidic as something like a carboxylic acid or an alcohol. So we have it on the scale of acidities, we have it being a little less acidic than alcohols, but more acidic than alkenes and alkanes, okay? So what we want to do is look at why those alpha hydrogens are more acidic than with regular alkanes and alkenes. So in this case here, we have the electron withdrawing ability of the carbonyl here, giving us an ability to pull away electron density. So if we had a base come in and remove one of these hydrogens here, that would create an anion on this single carbon. But that carbon is right next to that carbonyl. So we can have electrons kick in from that anion to go in between to form a carbon-carbon double bond, and we can have a negative charge on that oxygen. So just like an acetate ion where we have that negative charge spread across 3 atoms here, in an enolate ion, we have our negative charge spread across 3 atoms, but it's spread across 2 carbons and 1 oxygen in this case. Now that means that we can still do a lot of chemistry with that carbanion that we formed here, but it's nice and stabilized, the fact that it's over 3 bonds. Okay. So if we look at a relative scale of the acidity of hydrogens here, I'm going to blow this up real quick here. So one of the most acidic protons we can get by having that carbonyl associated with it is what we call a beta diketone. What that means is we have 1 ketone here, and then in between that we have a CH2 group in another carbonyl. And this hydrogen here is going to be the most acidic hydrogen that we can get from an enolate ion, okay? Notice this is even slightly more acidic than the hydrogen in phenol. Now, by converting this from this diketo compound to having 1 ester and 1 ketone on here, so this is a beta keto ester, meaning we're 2 carbons over from the ketone. We have an ester here. This oxygen acts as a little donating, therefore it decreases the acidity of this, and therefore it's harder to remove that because that acts as an electron donating group. So then let's go ahead and take the next step down. Let's replace one of those, this methyl group here, with another ester group. So now we have 2 esters. So we have the carbonyls, they're acting as electron withdrawing groups, but because we have esters instead of ketones, those esters are donating a little more density, meaning the carbonyls are not taking away as much density. Therefore, we're decreasing the acidity 1 more step right here, but it's still acidic enough to be removed by these bases right here. And then that takes us to the acidity of water, the proton in water and the proton in an alcohol. And then that takes us next to just above that. So the proton next to a ketone. So this would be acetone. This is that proton on an acetone or a ketone. And then it decreases again by adding that donating group of the alkoxy group here. So on this ester right here, it's just a little bit less acidic. And then we go to our traditional alkane. So we have our alkyne is first and most acidic at 25, and then our alkene, and then our alkane. Okay, so all of our enolate protons are more acidic than any of our other hydrocarbon protons. That's the important thing we have here. And by taking away the electron drawing groups found in esters, we can increase the acidity of the system such that when we get to this diketo compound, that becomes the most acidic alpha proton we can get. Oops. Okay, so now let's talk about the enolate ions formed, okay? We can either form them quantitatively, there we go. We can either form them quantitatively or under an equilibrium reaction. If we have a strong base, if we have a base that is stronger than the enolate base we form, then we will have what we call a quantitative removal of the hydrogen, meaning it's all shifted to the enolate, and the enolate can then do additional chemistry. If we have a weaker base than the system here, it'll form in an equilibrium and will only form a little bit of the enolate at a time. Okay. So let's talk about what we can do with enolates. Once we form this anion that's on that carbon, one carbon over from the carbonyl, the alpha carbon, by removing that alpha hydrogen, that acidic alpha hydrogen, we've generated an anion. And as we know in our substitution reactions and our reactions with ketones, if we have a nucleophile, it attacks a partially positive system or can displace a negative ion. And in the case of enolate ions, we already have in our system a partially positive group by having a carbonyl compound. So what can happen is we can have attack by the enolate ion onto that carbonyl carbon to generate an intermediate tetrahedral center with an alkoxide and retaining the ketone on the compound that was the enolate. All right, let's look at that very carefully again down here at the bottom. Okay, so we form the enolate here, and in this case, we're forming it with an ester. That anion on the enolate is attacking the carbonyl compound. When it attacks, the carbonyl compound opens up to give us this alkoxide, or the salt of the alcohol here, maintaining our carbonyl compound from our enolate. And in this case here, we can actually lose a group, in this case, lose an alkoxide to generate a new carbon-carbon bond, and we regained our carbonyl on our on our attacked species, and we end up with what we call a beta diketo compound because we have two carbonyls, and this is the alpha carbon, and so this is one carbon over. So we call that the beta dicarbonyl compound. Okay. So this reaction actually has a name. We call this reaction the Aldol reaction. And in the Aldol reaction, we take a compound that is either an aldehyde or a ketone. We react it with base. It creates an enolate ion, and then that enolate ion attacks another one of the same molecule, okay? So that's the Aldol reaction, okay? So in this first example of the Aldol reaction right here, we're gonna take an aldehyde, and we're gonna take ethanol, which is just the, it's a methyl group here, our carbonyl and our hydrogen here. Now, this hydrogen is not acidic. It does not come off in this. So that means that this is our alpha carbon, and these are our alpha hydrogens. So the first thing that's going to happen is we're going to remove this hydrogen here, giving us our enol, which then reacts with another one of the carbonyls. So this is our enolate that reacted to the carbonyl of the subsequent species. And we end up generating what we call a beta hydroxy aldehyde. So our aldehyde is still intact over here, and this is the alpha carbon. Now this is the beta carbon, which is one carbon over, and so we have a hydroxy group on that two carbons over from the carbonyl, giving us our beta carbon. So we have a beta hydroxyaldehyde. Now, if we did this with a ketone, the same thing happens, except that now we have a ketone instead of an aldehyde. So we have a removal of this hydrogen that creates the anion here. This anion then comes in here and hits the carbonyl, generating our beta hydroxy compound. And so we have our beta hydroxy ketone compound. Okay. All right, let's go into this in a little more detail and look at the mechanism step by step. Okay, it doesn't matter whether you start with an aldehyde or a ketone, the first step is the same. It's the formation of the enolate ion. Okay, so we're going to take a base of some sort right here, and we're going to take one hydrogen off of the of the alpha carbon here. Okay, so notice this is the carbonyl, so this is the alpha carbon, and notice that this is an aldehyde, so there's no alpha hydrogens over there because there's no alpha carbon there. So it must remove the hydrogen from this carbon on this side. That generates the enolate ion, which is then in equilibrium between the anion form and this. So this would be like the keto form, and this would be the enol form. Enol form, keto form. And so it's stabilized by doing that. But what happens is that the anion on the carbon is more nucleophilic, and therefore the anion on the carbon side will go through and attack the carbonyl on another compound to give us our beta hydroxy compound in this case. Note, in the PowerPoints on the track site, this image and the image on the next page have been swapped. So this is the correct image for this thing where we have attack of the nucleophile onto the electrophile to generate our beta carbonyl compound here. Now, if we move to the next step, and this is again correct here, what we have is the ability of this right here to now act as a base with water to generate our beta hydroxy compound. And in this case, we have an aldehyde. So this is our beta hydroxy aldehyde compound. But the mechanism is the same for the ketone. Formation of the enolate ion, attack of the enolate ion on the carbonyl of a neutral species, and then protonation of that new charged oxygen to give us our beta hydroxy compound. Okay, so now that we have this beta hydroxy compound, it actually very rarely stays that because these beta hydroxy compounds are very susceptible to just losing water or dehydrating. And when they dehydrate, we end up with what we call an alpha beta unsaturated carbonyl compound. In this case, it's an aldehyde, okay? So what's really cool about this is because this double bond is in conjugation with this double bond, it's really stable. So it makes it very easy to lose this product. Whenever possible, if you just slightly warm an aldol reaction, you end up eliminating water and going to the much more stable process. Note that that hydroxy keto compound, that hydroxyaldehyde compound, is in equilibrium with the two other species. So it can easily go back in that form unless you're actually moving forward and dehydrating to generate your final compound. So whenever you can generate a dehydrated product, you will get good yields in an aldol reaction. Okay, what other way do we have to make an aldol reaction work really well? Well, we know that when we generate the enolate, we can only generate an enolate from things with an alpha hydrogen. So if you were to use a strong base, can pull off all of the protons to generate your enolate, and then you added to it something that had no alpha hydrogens to it, then the enolate must react with that compound. It cannot exchange with that and make a different enolate, okay? So in the cross-aldol condensation, the idea is you take one carbonyl compound that has alpha hydrogens and you make your enolate, and then you add to it another compound that has no alpha hydrogens to it, and therefore it must react with that compound. Okay, so in this example here, we have acetone right here. It has a total of 6 alpha hydrogens. It has 3 on this side and 3 on this side. So it can form an enolate. Okay. If we look at the next compound over here, this is formaldehyde. Notice it has no carbons attached to that carbonyl. Therefore, there's no alpha carbons and there are no alpha hydrogens, meaning it cannot form an enolate. So the only thing that can happen when we add base to the system is this forms an enolate. This enolate can then react with this carbonyl compound to give you your hydroxy carbonyl compound. Okay. So how can we use this synthetically to our advantage? Well, by choosing our other substrate as the one with no alpha hydrogen. There's a lot of ways to do this. We can do it with aldehydes or ketones. And in this case, we are using formaldehyde because it has no carbons. So there are no alpha carbons, no alpha hydrogens. In this case, our carbon is a benzene carbon and has no hydrogens on it. In this case, we're using a different aromatic compound that also has no alpha hydrogens. And in this case, we're using a T-butyl group on our aldehyde here, such that there are no alpha hydrogens. These are all CH3 groups right here. And because there are no hydrogens on the carbon right next to the carbonyl, it cannot form an enolate. Therefore, it can only act as being attacked by an enolate. Okay, so can you do this on itself? Well, yes and no. Okay, so if you have two carbonyls or two aldehydes or two ketones or a ketone and an aldehyde on the same compound, and you can form a 5 or 6 membered ring, you can attack one side of the compound intramolecularly to the other side of the same compound to make a ring structure. Note, if you try to make a 4-membered ring or a 3-membered ring or a 7-membered ring or an 8-membered ring, those don't work because 4 and 3-membered rings are too strained and 7 and 8-membered rings have too many modes of freedom and they don't form, okay? So when we're doing that, we can actually form a couple different species depending on how long the chain is. So let's look at that possibility of forming an intramolecular aldol condensation with this diketone compound right here. Okay, now the first thing we want to look at is where are the alpha hydrogens, okay? So here there is an alpha hydrogen and we have the possibility of, we have a total of 3 possible alpha hydrogens on this end. And then on this case here, we have a possibility of 2 alpha hydrogens on that carbon. So we can form an enolate on this side or an enolate on this side. And then once we form that enolate, we can attack the other carbonyl. Okay, so let's look at how that might happen, okay? So in this case here, if we take our part right here and we take the most acidic hydrogens, those are the ones that are inside or are more substituted here, and we actually made our enolate out of this compound here, what would happen would be we would get this anion form here, and our intermediate state would form a 5-membered ring, okay? So what's gonna happen is that once we form our enolate here, it's gonna attack this other carbonyl, giving us our 5-membered ring. And then of course, because that 5-membered ring is pretty stable, 5 and 6-membered rings are most stable, it can lose water to give us our alpha beta unsaturated ketone in this case here. But what if instead of forming it here, and we did it in red here, instead of that, we took the proton off here and made our enolate there. Remember, we have 3 protons there to make our enolate. If we did that, we would form this enolate here. Then when it came in to attack the other carbonyl, we would end up with this 7-membered ring. 7-membered rings are not very stable, and therefore it will not form that intermediate. And so we actually don't form this 7-membered ring. It doesn't further dehydrate to give us this unsaturated ketone compound. So when we think about intramolecular interaction, we want to think of, okay, where can we pull off the hydrogen to make our enolate? Now, if that enolate attacks another carbonyl, does it make a 5 or 6-membered ring? If the answer is yes, then yes, we can do an intramolecular aldol condensation or aldol reaction. If it forms a 7-membered ring or bigger, or a 4-membered ring or smaller, it's not going to form that product, okay? So try to take off the other proton and see if it makes a 5 or 6-membered ring. If it does, it can form the intramolecular aldol. If it can't form that, it does not form the intermonoxide. All right, that's the end of section 1 of enolate ions. Continue on for our section 2.